In last few lectures, we have discussed in detail the concept of degree of freedom and the equipartition theorem. Now, after this detailed analysis of equipartition theorem in kinetic theory of gases, we are going to know about a new idea or new concept. In fact, this new concept is regarding the mean free path. In fact, the concept of mean free path finds its application while dealing with the phenomena which is called transport phenomena, which is a very important problem of kinetic theory of gases. So, this lecture on mean free path will be also divided in 3 or 4 parts to get the idea in concrete manner. And so, in this first lecture on mean free path, I am going to just give you an introduction, or you may say in this lecture we will simply define mean free path. What is this mean free path? We know only the definition, and after that we will see the different aspects regarding mean free path. So, to define the mean free path, first of all we will know some of the basic fundamentals, and then we will be able to define this very important quantity which is called mean free path. And as you know, our classical theory of kinetic theory is centered around the gaseous system. So here we will also talk about the gaseous system. You know, according to kinetic theory, the molecules of a gas are moving with very large velocities even at ordinary temperature, or you may say room temperature. In fact, when we find the average speed or the RMS speed or the most probable speed of gas molecules at ordinary temperature like 20 degrees C or 27 degrees C, or you may say room temperature, then it is found that the speed of gas molecules is of the order of 10 to the power 2 meter per second. In fact, this is not a small speed, this is a large speed in practice. But remember, if this much speed is possessed by a gaseous molecule, then what will happen? As you know, in the assumption of kinetic theory of gases, you have already studied that there is no force to restrain the motion of the molecules of a gas. And so, in general, we say that the motion of molecules of a gas is random. When you say random, it means it is aimless. It may move in any direction, or you may say this is just a chaotic motion. And in fact, as there is no force to restrain the motion of the molecule, so the gaseous mass content in a vessel should disappear in no time, you can say. If you consider that a vessel contains gaseous system, and since the molecules are moving with large speed like the speed of the order of 100 meter per second, and your vessel is of a small size, then the molecules from that vessel may escape in a very short interval of time. But the actual state of affairs is not like that. In fact, the molecules in escaping from the vessel takes a finite time or a long time, you can say. So there is just a contradiction. And what is that contradiction in the actual state of affairs and the theoretical aspect which in accordance with kinetic theory should be? Let us see here. In fact, you can say that the actual observations, as we are aware that the top of a cloud smoke holds together for hours. If there is a cloud of a smoke, its top remains actually for hours and hours. But according to kinetic theory, as the molecules move or particles move with large speed, this smoke particles should be removed in a very small time interval. But in spite of it, we see that the cloud of smoke holds together for hours. So definitely there is a serious objection against the assumption that molecules of gas move with large rectilinear velocities, and hence there must be some factor which prevents the free escape of particles. So this was actually the problem, that why the particles or the molecules of the gas do not escape from a vessel freely in no time. Actually, this difficulty was solved by a well-known physicist without whose work you can't think thermal physics, and that scientist is none than Clausius. Actually, Clausius resolved or solved this problem. How Clausius solved this problem? Let us now see some of the facts here. Actually, this is just an introduction, so there will be almost no calculation. So I have mentioned the very important facts here for your convenience, and let us now understand this fact. How Clausius resolved or solved this problem, that the molecules of a gas will escape in no time from a vessel or should escape. But actual state of affairs is what? The actual state of affairs is that the molecules takes a large time for escaping from the vessel. So how this problem will be solved? As I have told you, that this solution was given by the famous scientist Clausius. Actually, according to Clausius, the molecules of a gas has a finite size. They are not just geometrical masses. And Clausius introduced the idea of collision between the molecules. In fact, if molecules were truly geometrical points, then there should be no collision between them. If the molecules will be treated just like a geometrical point, it means having no dimension, neither length nor breadth nor height. In that condition, collision should be not effective. There will be no collision. But actually, according to Clausius, the gaseous molecules are not just geometrical points, but they have a finite size, although that is very small, but we can measure the diameter or the radius of the molecule and it is of finite size. And so definitely during the random motion, the molecules get collided with one another. So you can say that due to the finite size, the molecules collide with one another, and during the collision, a large impulsive force acts between the molecules, and due to that large impulsive force, the direction and the magnitude of velocity of the molecules get changed. जब कभी भी कॉलिजन होगा, एक लार्ज इम्पल्सिव फोर्स काम करेगा और उसके कारण मॉलिक्यूल का जो डायरेक्शन है मोशन का, उसके वेलोसिटी का जो मैग्नीट्यूड है, दे गेट एक्चुअली चेंज रैंडमली. But what about the situation when the molecule is not suffering a collision? In fact, between two collisions, successive collisions, you can say, let us consider that at this point a collision is suffered by the molecule, at this point another collision is suffered. So when the molecule travels between these 2 points, 1 and 2 are the point of site of collision. So between these 2 points, actually the molecule is not acted upon by any force. Here motion is force free, and you know, according to Newton's first law of motion, if motion is force free, that is no force is acting on our system, then path of the motion must be a straight line. So you can say that the path followed by a molecule between two successive collisions must be a straight line. Must be a straight line. Now, as the molecule suffers a large number of collisions while traveling in a gaseous system, and during every collision, the direction of velocity and its magnitude change abruptly, or you can say randomly. So, as a whole, the total path of motion of a molecule will be just a zigzag path, as I have shown this in this figure. You can say this figure, and from this figure it is evident that the molecule starting from point A. See this figure. If you consider that a molecule starts its motion from this point A and moves along AB, this AB, and suffers a collision at B, you can see the molecule which starts its motion from A moves along AB and suffers a collision at point B, or you can say with a molecule at B. Then when the direction as well as magnitude of its velocity is changed, and after changing the direction of velocity, it moves along BC. You can see this figure. Due to collision at B, the molecules now moves along BC. Again, you can see that this molecule suffers another collision at C, and after that its direction of motion again randomly changes, and now it moves along CD, and at D again it suffers another collision, and due to that collision now the molecule moves along DE. So in this way you can say that after traveling these distances A, B, C, D, D, E and so on, actually the molecule follow a zigzag path. As a whole, you can see this figure that if we consider that this point, final point I am showing here, just like suppose Zn. So the path followed by the molecule between point A and this point Zn, you can see as a whole this path is a zigzag path. But see the path between two successive collisions. Let us consider between points A and between point B. You can see this path is straight. Again between points B and between point C, the path is straight. Again between point C and between point D, the path is straight. Actually, these straight paths, when the molecule does not suffer any collision, or no force acts on the molecule between these two collisions, between these two successive collisions, or along moving this straight path. So such a path is called free path. So AB, you can say BC, CD and so on. What are these? These are called free paths. These are called free paths. When you say free path, it means free from force or free from collision. It means during the motion along a straight path, there is no force acting on the molecule and the molecule is not suffering any collision. So such a path is called free path. Now, can you think that all these three paths will be of same length? No, definitely not. It is just a chance that any two free paths may be same, but as a whole you can say that in general the length of the free paths will be different. So let us consider this AB is of lambda 1 length, BC is of lambda 2 length, and this CD is of lambda 3 length. And finally we consider this path, and this is of length lambda n. So this lambda 1, lambda 2, lambda 3 and so on lambda n, these are actually known as free paths. So lambda 1, lambda 2, lambda 3 and so on lambda n. If there will be n collision, there will be in fact n free paths, lambda n. These are called free paths. And as I have told you, these free paths may be in general different. So in physics, we find the average value of these free paths because this quantity is varying. So for its use, it is necessary to know the average or mean value of these free paths. When we define the mean value of these free paths, we denote it by the symbol lambda, and then this lambda is called mean free path. Mean free path. So in this way, now we can define what is this mean free path. First of all, we will define it, and then in quantitative manner we will write the expression for it. So now after this idea, you can define this mean free path in this manner, that the mean free path is the average distance through which a molecule can travel through a gas without colliding with another molecule. The mean free path is the average distance through which a molecule can travel through a gas without colliding with another molecule. And so this is actually the mean of free paths, you can say in simple manner, and so it is also called average run between two collisions. Average run between two collisions. So simply it is mean or average. Mean or average of free paths. And as you have seen that this lambda 1, lambda 2, lambda 3, so on, lambda n are free paths. Are free paths. So mean free path. Mean free path. If we denote the mean free path by the symbol lambda, then what will be this lambda? This is simply the mean of free paths. And lambda 1, lambda 2, lambda 3, so on, lambda n are free paths. So its arithmetic mean will be what? This will be simply lambda 1 plus lambda 2 plus so on plus lambda n divided by n. N is actually the number of free paths, or you may also call that this is number of collisions suffered by the molecule. N is here number of free paths, or the number of collisions. Number of collisions suffered by the molecule. Suffered by the molecule. And as you know that there will be a large number of collisions because a gaseous system consists of a large number of molecules. So actually this quantity, that is a mean free path, is actually a statistical quantity. And if it is an statistical quantity, its value will certainly depend on to some extent on the method of finding the average. Since as I have told you that lambda चूंकि एक स्टैटिस्टिकल क्वांटिटी होगा लार्ज नंबर ऑफ कोलिजन होने के कारण, सो इसका जो वैल्यू होगा वह इस बात पर डिपेंड करेगा कि आप मीन निकाल किस तरीके से रहे. व्हाट इज योर मेथड ऑफ फाइंडिंग द एवरेज. ऑन दैट फैक्टर द वैल्यू ऑफ मीन फ्री पाथ विल डिपेंड. So let us note this point. This is a very important point. So I am noting it in brief for your convenience that this lambda is a statistical quantity. A statistical quantity. And if it is a statistical quantity, its value depends to some extent on the method of finding mean of lambda 1, lambda 2, so on lambda n. So you can say there is a certain arbitrariness in our standard in defining a mean free path. However, if a reference is made to a group of molecules instead of a single molecule, then mean value of all free paths that are executed in a given time by all molecules in a given volume is taken. Then we shall actually define this mean free path in a particular manner. So now let us consider that our gaseous system has a finite volume, and for calculation we consider that the volume under consideration is not very large but and not very large and not also very small. So we in general we consider that there is a finite volume of our gaseous system. So in this condition, first of all, to get the expression for mean free path, first of all we will define the average speed of the gaseous molecule. Now you can see what will be the average speed and how we will define it. Since you have seen that the total distance covered by the molecule during this collision will be what? That will be simply the sum of all free paths. And if you consider a time interval in which that path is traversed by the molecule, then simply dividing the total distance by total time, we will get actually the average speed. So now you can say, now average speed of gas molecule. You know, average speed is defined as how? This is defined as total distance described or traversed. Total distance described or traversed over total time taken. Total time taken. Now as you can see, if there is n collisions, during this n collision the total distance traversed by our molecule is what? that will be simply sum of all free paths, lambda 1 plus lambda 2 plus so on plus lambda n, and divided by total time. Let us consider the total time taken by the molecule in this journey is equal to t. We assume it. So V average will be equal to this much. And so you can now write the sum lambda 1 plus lambda 2 plus so on plus lambda n. This will be equal to average speed V times t. Say this is equation 2. Now you can see our definition of mean free path, which is in equation 1. So now we will use equation 2 in this equation 1. So using equation 2 in 1. So using equation 2 in 1, we get mean free path lambda. You have seen that is lambda 1 plus lambda 2 plus so on plus lambda n over n. But from this equation 2 you can see this sum is what? This is average speed V times t and over n. Now if you multiply this average speed to the time taken in this journey, then actually we will get the total distance traveled by the molecule in n collisions. And if you consider that distance is equal to s, then this will be simply equal to s over n. S over n. There should be n here. And you can see what is this s? S is equal to average speed times t, and this is actually the total distance traveled in n collisions. So this is just a defining equation of mean free path. If whenever we will find the expression for mean free path, we will use such an idea which we have developed in this lecture. To get the value of mean free path, we will simply divide the total distance traversed by the molecule by total number of collisions suffered by the molecule. And so using this equation 3, we can find the expression for mean free path. But as I have told you earlier that in this lecture we are just going to define the mean free path, not a detailed analysis. In fact, in the forthcoming lecture, first of all we will find the expression for mean free path, and then we will see something extra in other lectures.